Welcome to Veteach. In this session, we are going to start Unit 4. So, Unit 4 contains three major topics: quantum mechanics, electron theory of metals, and band theory of solids. So, in this session, we are starting quantum mechanics. So, in this quantum mechanics, we are going to discuss the behavior or motion of the microscopic particles. So, this behavior of the microscopic particle plays an important role in different properties of the metals, like physical properties, chemical properties, optical properties, magnetic properties, mechanical properties, and etc. So, in order to understand the behavior of these microscopic particles, initially Newtonian mechanics was applied, so Newton's laws of motion, and applying this Newtonian mechanics results so many failures in understanding the properties of the material. So then a new branch of physics was developed, which is quantum mechanics. So in this quantum mechanics, we are going to discuss about matter waves, and this concept or hypothesis was developed by de Broglie. In order to understand the behavior of the microscopic particle, de Broglie approached in a different way. So already we know that electrons, atoms, molecules, proton, nucleus, all these are particles. Now de Broglie extended the idea that the particles, what we are calling so-called particles like electron, nucleus, proton, atom and molecule. In addition to this particle nature, they also possess wave nature. And he used the concept that we know that light, which is electromagnetic radiation, exhibit dual nature. Light exhibit dual nature. So we know that light exhibit a particle nature during photoelectric effect and Compton effect, and it exhibit wave nature during the phenomena of interference, diffraction and polarization. At particular instant of time, the light may exhibit either wave nature or particle nature. Suppose when the light strikes an obstacle whose size is comparable to its wavelength, it exhibits bending, and which is the wave nature of the light. And the same light, when it incident on solar cell, it exhibits photoelectric effect, which is the particle nature. So depending upon the circumstances or situation, the particle either exhibit particle nature or dual nature. So the particle never exhibit both nature at the same time. So de Broglie extended the same idea, how the photons have both particle nature and wave nature, and he extended the same idea to the material particles like electrons, protons, nucleus, atoms, molecule. These material particles also exhibit dual nature, and the waves that are associated with the material particle or moving material particle, he named as matter waves or de Broglie waves. So matter waves means the waves associated with the moving particles are called matter waves. So here the particles are, material particles are electrons, protons, nucleus, atoms, molecules. So these microscopic particles also exhibit both particle nature and wave nature. And the hypothesis proposed by de Broglie is called de Broglie's hypothesis of matter waves. De Broglie's hypothesis of the matter waves. And this hypothesis is like this: every material particle like electron exhibit dual nature. So since electron is a particle, it exhibits particle nature. Since it having mass and velocity, it is a particle. Simultaneously, at particular instant of time, this electron also exhibit wave nature in addition to particle, and this is the main concept of de Broglie hypothesis. So de Broglie proposed that every metal particle exhibit or possess dual nature. Now, when the electrons or metal particles exhibit wave nature and particle nature, so he proposed, according to his hypothesis, that metal particle exhibit wave nature under motion. So when the particles are under motion, they exhibit wave nature. For example, already we studied from earlier classes that electrons revolve around the nucleus. Since electron is under motion and it is revolving around the nucleus, as long as it is revolving around the nucleus, it exhibits wave nature. And the electron is under motion, it possesses wave nature. And the wave associated with this electron is called matter waves. Is called matter wave. When the particle exhibits wave nature or it possesses waves, it should have some wavelength, and that wavelength of the matter waves is called as de Broglie wavelength. And the de Broglie wavelength lambda is given as lambda is equal to h by mv. Lambda, which is called de Broglie wavelength of the particle, is equal to ratio of Planck's constant h by mv. And this is called de Broglie wavelength. H is called Planck's constant, whose value is 6.625 into 10 to the power minus 34 joule second. M is called mass of the particle. If the particle is electron, mass of the electron. If the particle is proton, mass of the proton. And V is called velocity of the particle. The product of mass and velocity can also be given as momentum. Therefore, de Broglie wavelength can be given as ratio of Planck's constant and momentum. And this P is called momentum of the particle. So, this is about de Broglie. And we can derive the expression for de Broglie wavelength. So, while deriving the expression for de Broglie wavelength, so de Broglie consider two important concepts. One is Planck's theory of radiation and Einstein mass energy relation. Both are related to energy of the photon. So, he considered the photon and derived the wavelength for the material particles. So, why he considered photon? Since the photon is a particle, it having mass and velocity, and simultaneously the photon also exhibit wave nature. So, if the wavelength of the photon, the idea of the wavelength of the photon can be extended to the wave nature to the particle also. So, from the well-known theories from Planck's theory of radiation and Einstein mass relation, we have the energy of the photon. From the Planck's theory of radiation, the energy of the photon can be given as E is equal to h nu. E is the energy of the photon, h is the Planck's constant, nu represent the frequency of the photon. So, the wave velocity or light velocity can be given as C is equal to product of wavelength and photon, frequency of the photon. From here, the frequency can be given as nu is equal to C by lambda. So, the energy of the photon from the Planck's theory of radiation can be given as E is equal to hc by lambda, and this one can be considered equation 1. From Einstein mass energy relation, the energy of the photon can be given as E is equal to mc square. The energy E value from the Planck's theory of radiation represents energy of the photon, and E from the Einstein mass energy relation, E represents energy of the photon. So, from equation 1 and 2, LHS are equal, simultaneously RHS also will be equal. So, equating RHS of equation 1 and equation 2, we have mc square is equal to hc by lambda. So, solving this one, we have the wavelength of the photon, h lambda can be given as h by mc. Here, the h represents Planck's constant, m represents mass of the photon, c represents velocity of the photon. So, the photon possesses dual nature. The idea of the wavelength of the photon can be extended to the material particle, which is having a mass m, moving with velocity v. So, therefore, the wavelength of the matter wave associated with the moving particle can be given as lambda is equal to h by mv. And here, the h represents Planck's constant, m represents mass of the particle, v represents velocity of the particle. The product of mass and velocity can be given as momentum, therefore, lambda is equal to h by p. So, this is de Broglie wavelength of the particle. And if you extend this formula in other terms, we can get the expression for de Broglie wavelength in terms of kinetic energy of the particle, or the de Broglie wavelength of the particle which is accelerated by external electric potential, and the other terms. If you extend the same idea here, the de Broglie wavelength in terms of kinetic energy. So, we know that the kinetic energy of the particle capital E can be given as half mv square. So, this can be write like this here, m square v square by 2m is equal to kinetic energy of the particle, and therefore, m square v square is equal to 2me, mv is equal to, which is equal to momentum is equal to square root of 2m into kinetic energy. So, substituting the value of mv in this equation, we have de Broglie wavelength in terms of kinetic energy lambda is equal to h by square root of 2m into kinetic energy of the particle. So, this is the de Broglie wavelength in terms of kinetic energy, de Broglie wavelength in terms of applied potential. Suppose we have a metal For example, it is considered conductor which contains free electrons. So if you apply a voltage of capital volts, capital V volts, if you applied an external potential of capital V, the electrons are drifted to move in a direction from negative terminal to positive. And the kinetic energy which is attained by this electron due to applied potential capital V can be given as kinetic energy is equal to product of applied electric potential and charge of the carrier. So if we substitute the kinetic energy VQ in this equation, we have de Broglie wavelength in terms of applied potential, which is given as lambda is equal to h by square root of 2m VQ. So here the capital V represents applied potential. In equation 3, the small v represents velocity. So while using these formulas, we need to be clear that the small v in the formula represent velocity of the particle and capital V represent the applied potential to the charge or the particle. In terms of thermal equilibrium, the de Broglie wavelength can be given as lambda is equal to h by square root of 3m kT. The k represents Boltzmann constant and T represents absolute temperature. And if you attain the de Broglie wavelength for the particle of electron which is accelerated by potential V. So this is the mostly used particle electron. For this electron which is accelerated by external potential V, for this electron the de Broglie wavelength will be like this. So here the electron is accelerated by potential difference capital V. So from the de Broglie's wavelength, the de Broglie wavelength of the electron which is accelerated by potential V can be given as lambda is equal to h by square root of 2m VQ. So for the particle regarding electron, for the electron, we know the mass of the electron which is 9.1 into 10 power minus 31 kg and the charge of the electron which is 1.6 into 10 power minus 19 coulombs. And since the Planck's constant is a constant value which is equal to 6.62 into 10 to the power minus 34 joule second. If we substitute these three values in this equation, we get the de Broglie wavelength for the electron which is accelerated by potential V. Since the potential V is a variable term, so we make this term an outside and we substitute all the values of Planck's constant, energy of mass, charge of the electron, mass of the electron. If you substitute in the expression of this, we have lambda is equal to 6.625 into 10 to the power minus 34 divided by square root of 2 into 1.6 into 10 to the power minus 19 into 9.1 into 10 to the power minus 31 into 1 by root V. If we solve this numerical value, so the numerical value will be lambda is equal to 1.227 into 10 to the power minus 9 divided by root V meters. So we know that 1 angstrom is equal to 10 power minus 10 meters. So in order to get here 10 power minus 10, what we do is we multiply and divide with 10. So here we have 1.227 into 10 power minus 9. We are multiplying and dividing with 10 here into root V meters. So from here 10 power minus 9 by 10 we have 10 power minus 10. 1.227 into 10 we have 12.27. So rearranging the terms we have lambda is equal to 12.27 into 10 power minus 10 meters divided by root V. So 10 power minus 10 can be given as 1 angstrom. So therefore the de Broglie wavelength for the electron can be given as lambda is equal to 12.27 divided by root V angstrom. So this is the practical case where we use the de Broglie wavelength of the electron in designing the microscope called electron microscope. So here the de Broglie wavelength of the electron is inversely proportional to the square root of voltage. So if you apply the higher voltages in terms of 1 lakh volts, 2 lakh volts, the wavelength of the electron decreases, and which is used to study the structure of the materials or observe the structure of the material by using electron microscope. So this is the important concept of de Broglie wavelength of electron, which is the background principle for the construction of the electron microscope. Thank you.